We all know what ice is, right? Well, did you know that there are actually 19 different types of ice? And as it turns out, only one naturally occurs on Earth, or there are trace amounts of others, but mainly the one. So, what are these other types of ice and where are they occurring? I'm sorry if I'm already starting out the video yelling, but I got so surprised and excited when I heard that there are 19 different types of ice. I mean, how cool is that? So in this video, I'm going to be talking about what ice is, why ice floats, the color of ice, why it appears certain colors, the different types of water ice, the 19 different types that I just mentioned, and I specify water ice here because this video is not about different types of frozen liquids. It's actually all about different types of frozen water. So I specified that we're talking here about water ice only. And then I'll talk about dense ice and the potential presence of dense ice that does not float on other worlds, which is really cool. And then lastly, I mean, I would get ripped apart in the comments if I did not discuss snowflakes in an ice video. So we will end out the video talking about ice in air, or different types of ice that form in our atmosphere and fall down onto our heads. So let's get started. Now, for some reason, this concept is weird to some people, but ice is a mineral. In other words, it's a naturally occurring crystalline inorganic solid with an ordered structure. And as we all know, it forms below the freezing temperature of water, which is 0 degrees Celsius and 32 degrees Fahrenheit. But this depends on pressure and the presence of impurities. For example, the melting and freezing temperature of water changes at pressures that are different than atmospheric pressure, the pressure at Earth's surface, and at different concentrations of impurities, for example, salt. And I actually have a video, my phase diagram video, where I talk about the different melting and freezing temperature of water with different concentrations of salt. So I'll link it up to the top right if you want to check it out. So why is ice important, especially to a geoscientist? Well, ice plays a key role in Earth's water cycle and biogeochemical cycles. So not only does ice hold an enormous amount of fresh water and control, at least partially, the movement of water between different reservoirs, but it also plays a major role in biogeochemical or biological, geological, and chemical cycles on Earth. What does this mean? Well, the ice on Earth in glaciers and ice sheets isn't static. It's freezing, it's melting, it's progressing, it's retreating, it's transporting all the while chemicals and rocks within the glaciers. It's carving valleys. It's doing all these geological and chemical transport and depositional processes, and it's also majorly affecting the biosphere, but I'll talk about how it affects the biosphere more in a later slide. Ice occurs naturally on almost every single body in our solar system, and as I mentioned earlier, 19 phases, at least 19 phases exist depending on different temperature and pressure conditions. But before we talk about these different phases, let's talk a little bit about the ice that we know and some of its properties that we're familiar with. For example, ice floats. What's up with that? Because normal solids get more dense when they freeze or crystallize from their liquid phase, and ice is not this way. It kind of spreads out as it freezes. This is because water, or H2O, consists of oxygen covalently bonded to 2 hydrogen atoms in the molecules that are H2O. And between these covalently bonded H2O molecules, we actually have a different type of bond that holds the molecules together. These bonds are called hydrogen bonds, and they're weaker than covalent bonds and much longer. And this holds together the ice and the water structure. But the difference here between when water is liquid and when it's solid is that when it's solid, it's crystalline. It has a crystal structure, and the structure is hexagonal. And so it has to spread out to form this crystalline structure, because this hexagonal structure is built with the hexagonally organized hydrogen bonds connecting the water molecules, and these are much more spread out compared to when it's in its liquid form. It's just all these molecules kind of closer together, and there's a few hydrogen bonds here and there, but they're not in this crystalline form because it's liquid. So when it forms the crystalline structure, it spreads out and density decreases. And that is why it floats on water. It's less dense than the water itself. It is about 8.3% less dense than its liquid form, and this equates to, as it freezes, about a 9% volume expansion. And this expansion of water as it freezes causes a few things, including freeze-thaw weathering, weathering in which water seeps into cracks and spaces in the rocks, and then when it freezes, it spreads apart those cracks and then melts again and goes away. And in these regions where you have, seasons, which is most regions, you have water getting into rocks and causing this freeze-thaw weathering and breaking down the rocks quicker that way. This expansion of freezing water also causes the flooding of houses when our pipes burst, and that is really annoying to us, but just the way water was made. But if it wasn't made the way that it is, less dense as ice, we all life on Earth might cease to exist. So thank you, water. Even though you flood our houses, it's okay. You help us evolve, so thank you. And lastly, and as just mentioned, most importantly, ice floats on water because it expands when it freezes. If it didn't, bodies of water would freeze from bottom up and potentially prevent all benthic life from existing at all. And benthic or bottom-dwelling life on the ocean floor is where we all came from. So that could obviously cause life on Earth to cease to exist. Now, there might be some other kind of life that would have evolved, but would it have gotten so complex, multicellular, large, intelligent? Maybe not. It might just be a slimy microbe world if ice was different on Earth. So now we know why ice floats, but why does ice often appear a bluish, greenish color? Well, ice, just like water, absorbs light at the red end of the spectrum, but it's at slightly lower energies than what liquid water absorbs. So ice appears bluish with a slightly more greenish tint than water. Remember that the absorbed light is not what you actually see. You see the reflected and transmitted light. So basically everything that's not absorbed. And this color effect intensifies with greater thickness. Other colors in ice, other than greenish bluish, occur because of impurities. Such impurities can be things like sediment, algae, air bubbles, and this can cause colors of ice ranging from brown, gray, green to red even. There's red snow in some parts of the world that contains these special type of algae that are red, and so the snow appears red, but it's not the snow, it's actually the algae that is the red part. So I just think that's super cool. And finally, getting to these 19 phases or types of ice that I teased at the beginning of the video. Basically, if we alter the temperature and pressure conditions under which ice forms or water freezes, we can create these different types of ice that are differentiated based on their crystal structure, their proton ordering, and their density. The type of ice we are familiar with on Earth and in our ice cube trays is ice 1H, or hexagonal ice, like we showed at the previous slide with the hexagonal formation of the hydrogen bonds. That's the type of ice that we are familiar with and interact with on a daily basis. However, there are minute traces of cubic ice that naturally occur on Earth, as well as tiny inclusions of ice 7 that have been found in diamonds. But again, remember, diamonds form in a really high pressure environment, so it's not likely to be found on Earth's surface. But even though there are so many different types of crystalline ice forms, there are also amorphous ice phases that exist. So non-crystalline, non-ordered, crystal-structured ice also exists. You can see the kind of random structure of what is called HDA here. This is high density amorphous ice. And this, as you can see, is much denser and obviously less crystalline or non-crystalline compared to our ice 1H that we're familiar with. Water in the interstellar medium, or space, is dominated by amorphous ice, and thus this amorphous or non-crystalline ice is probably the most common water in the universe. And we've actually found and predicted, based on temperature pressure conditions of space and other worlds, that ice 1H, the ice that we have here on Earth, is probably extremely rare in space and on other planets and moons. But amorphous ice isn't even just one type of ice. There are 3 different forms. Now, when I read this, I was flabbergasted because, typically minerals, guys, are differentiated if they have the same composition, in this case H2O, and there's different phases, or what we call polymorphs, different structures. They're differentiated based on crystal structure. So like when an ice form has no crystal structure, how could you have three different types? Like it's one type, it's non-crystalline. But actually, they differentiated these three different types based on density. Now, there's only two listed here because I couldn't find a picture of the crystal structure of the third. But, we have our crystalline ice 1H shown here, and then our LDA and HDA. So we remember HDA is a high density form of amorphous ice, and LDA is low density. Now, LDA can be formed at atmospheric pressure or even below. However, HDA and VHDA, let me sit here for a second while you guess what that means. It just means very high density amorphous ice. Those are formed at higher pressures, obviously, because if you have higher pressures, you'll form a more dense structure. LDA can be formed by cooling liquid water extremely fast, or depositing water vapor on cold substrates, or even just by heating HDA or VHDA at ambient pressure. Now, I know I talked about all the different 19 types, or I didn't talk about them, but I mentioned that there are 19 plus different ice phases, but they're, believe it or not that exciting. So I have them listed here if you want to pause the screen and kind of look at the different structures and the different proton ordering things of these different ice phases, knock yourself out. I'll list links below in my description box if you want to check out the references directly that talk about these phases. But the only thing that I want to highlight that I think is the real interesting thing to glean from these 19 different phases of ice is the fact that this ice 3 here is the least dense form of the high pressure phases of ice, which are pretty much all the other phases, and it's still denser than water. In other words, most phases of ice don't float in water, even though that is the only ice that we're familiar with. We are familiar with ice 1H, and that is all. But most phases actually sink in water, which is crazy to think about because that would change the entire way that things are on Earth. That would change Earth drastically if that was the case on Earth. So let's talk a little bit about the consequences of dense ice potentially being present on other worlds, and if that kind of prevents the presence of life on those worlds, and whether, if we detect this kind of ice on a world, should we even explore it? So ice, obviously, as I mentioned before, is an important component of global climate, particularly in the water cycle. Glaciers and ice caps on Earth store 70% about of freshwater on Earth. And sheets of ice that are floating, because we're on Earth and we have ice 1H, sheets of ice that float on the sea surface not only allow things like polar bears and seals and stuff to get on top of them and move around that way, but also allow light to pass through enough to fuel biology below the ice sheets, but also protect these organisms because the ice insulates the water underneath and protects the organisms from extreme weather conditions. Now imagine if we had the opposite scenario. Imagine if this ice was not on the surface, but started to form from the bottom and freeze upward. Would it prevent life? This is precisely why the prediction of different ice phases on icy moons like Ganymede, Europa, Enceladus, Titan, Callisto, Triton, there are just so many icy moons in our solar system that have the potential for a subsurface ocean and life. But if we are able to predict that there are dense phases of ice in these oceans potentially, that might heavily influence where we go to search next. Ganymede and Callisto, for example, are two moons of Jupiter that have been suggested to potentially contain dense ice that covers their sea floors. Now, let me clarify here. We haven't gone to these worlds, drilled down into their oceans, and seen ice on the seafloor. We predict these things based on the different temperature and pressure conditions that are predicted for such a world. Now, I do have a video where I talk more about how we know there's oceans present on, for example, Europa, which I'll link up to the top right because I talk way more about that and how we detect the presence of a liquid water ocean from remote sensing in that video. So check that out if you're interested. But the gist here is if dense ice is covering these worlds' sea floors, then that prevents water-rock interactions. The direct interaction between the rocky mantle and liquid water is very important for life as we know it, at least, because For life as we know it, that creates what we call chemical energy, or basically chemical compounds, because of the dissolution of these rocks, that can give life a means to make energy, and a means to metabolize, and a means to live. So if there's the presence of dense ice on these worlds, it makes the presence of life much less likely. But even if there is dense ice, would it be covering the entire seafloor? It could be possible that there are some areas where there are water-rock interactions, but is it unstable? Does ice form seasonally in those areas? We don't know, anything. That sounds really bad, but in other words, like, if you're interested in going into this research, do it, because we need to know a lot more. Finally, let's get to ice in the air. And this is where we'll get into things like snowflakes, which are super cool, and I was not aware of just how cool. So before I get into ice in the air on Earth, I want to mention that I do have a video, or no, two videos actually, about glacial depositional processes. I'll link the first one up to the top right so you can check it out. That's if you want to know more about ice on land and in the oceans, how it moves around, how it carries sediment, how it affects sediment, how we see ancient evidence of glaciers and predict, different ice ages, whatever. But in this video, we'll just be talking about ice in the air. And the first thing we'll talk about in terms of ice in the air, quote unquote, is Rime. Rime is ice formed on cold objects when drops of water condense on these things and then crystallize on them. It's typically observed in foggy weather when the temperature drops at night. If you've ever seen these beautiful patterns of ice on your windows when you wake up on a cold morning, I mean, that's Rime, and it's freaking cool, guys. I tried my darndest to look up why exactly ice forms these needle-like structures around branches of trees under certain conditions, and I couldn't find anything. I mean, it might be straightforward in just that ice that we have on Earth forms different shapes, and they're in a few major different classes that I'll mention in a later slide when we talk about snowflakes. But one of the major classes is needle structured, and so it obviously prefers, or typically when I see branches, they seem to prefer the needle structure of ice. I don't know though what the reason is for that and why ice forms these needle structures on branches, but I think it's just beautiful. So I wish I could have found something that explained why that happened for you guys. If anybody knows, please drop it in the comments. We are all curious. But anyway, soft Rime contains a high proportion of trapped air, so it has a density that is about 1/4 of pure ice, or much less than pure ice typically. And now moving on to ice pellets. So now we're kind of moving into the realm of things falling, ice falling from the sky rather than just condensing onto things. And ice pellets are exactly what they sound like. They're small balls of ice, typically small translucent balls of ice, and they're also referred to as sleet in the US. Apparently, in British English, sleet refers to a mixture of both rain and snow, but in the US, sleet refers to ice pellets, and ice pellets are smaller than what we typically refer to as hail. And graupel is different. Instead of ice balls, it's snowflakes that collect super cold water droplets on their outer surface. Now, I'm going to mention this term, super cold, I think a couple more times throughout this video. All super cold means is that it's water existing at a colder temperature than freezing. The reason that it's liquid and it's colder than freezing in terms of temperature is, from what I understand, because to freeze, it needs something like a surface or a grain to nucleate around. And so until the liquid water finds the snowflake to crystallize on, it is just there as super cold water. Then it falls down as this big puff of snow-like thing because it's condensed and crystallized around the snowflake. So the formation of ice pellets, I believe, does a better job of differentiating ice pellets from hail, and that's because ice pellets form when a layer of above freezing air is sandwiched between two layers of below freezing air, and snowflakes fall from the below freezing, the sub-freezing air above it, and then they fall into the warm layer. They melt either partially or fully, and then in the lower cold layer, again, they refreeze into ice pellets. If, however, the lower layer of sub-freezing air is too small or too thin, and the warm layer is thicker, the precipitation won't have time to fully refreeze, and instead freezing rain will happen. Now, hail, on the other hand, which is typically greater than or equal to about 5 millimeters or 0.2 inches, forms in storm clouds when supercooled water droplets freeze onto nuclei or just a grain of some sort. And then the storm's updraft blows the hailstones into the upper part of the cloud, and this updraft eventually dissipates and the hail falls back down and then is lifted again into the next updraft, and the hailstones gain a layer of ice each time they're blown by the updraft into the upper part of the cloud, and this causes them to grow increasingly larger with each ascent. And once the hailstone becomes too heavy to be lifted by the updraft again, it falls to the ground, and that's why they're a bit bigger and they're different in terms of formation mechanism to sleet or ice pellets. And the most commonly reported hail size is golf ball size. Now, I was surprised about this because where I grew up, at least in North Texas, we typically got hail that was big, but much smaller, I think, than golf ball. I think golf ball would be a little bit of an over exaggeration. So maybe when I'm thinking of a sleet, but the other thing that came to my mind is maybe when they say most frequently reported, it just means that people don't care about smaller hail and won't report it. So I don't know. Now, in terms of maximum or upper limit of hail, it seems that hailstones can grow to 15 centimeters or 6 inches and weigh more than 0.5 kilograms or 1.1 pounds, which seems to me to be pretty huge. Finally, getting to snowflakes. The formation of snowflakes is kind of like hail in that it nucleates around a mineral or organic particle in some way in a moisture-saturated sub-freezing air mass. But I also wanted to note here that the ground temperature does not have to be this cold, because everybody's always wondering, what temperature does it have to get down to in order to snow? Well, the air up in the sky where it's forming has to be sub-freezing, but the ground doesn't have to be. I think just the other day, El Paso got some snow that was in like 40 degrees, so it can be above freezing where you are to actually get the snow to fall. But then when it hits the ground, it will melt, or at least where I'm from, that's always the case. In any case, snowflakes grow after they nucleate by accretion in hexagonal formations, which is why snowflakes always, well, I shouldn't say always, but tend to have a hexagonal or a six-pointed kind of star look to them. And the complex shapes of snowflakes emerge as the snow moves through different temperature and humidity zones, which cause snowflakes to differ in detail. Now, I want to highlight the video I watched as I was doing research for this video, which was Veritasium's video. If you've never seen Derek or Veritasium and his videos, oh my gosh, they're amazing. I've loved him since I was a little girl. Well, not that little, he's pretty young, but anyway, he has a video that I will link up to the top right for you that talks about snowflakes and how they form these different shapes, and he highlights a scientist in that one that kind of shows him how he can form snowflakes in the lab by changing temperature and humidity. It's really cool. So I found a lot of different classifications or proposed classification systems for snowflakes, but I kept seeing these 8 broad classifications that were suggested by this 1966 paper show up, and I'll link the paper below for you. And these include needle crystals, which is classified with an N, columnar crystals, which can form individually or be kind of radial columnar structures, plane crystals, which are in a plane and are those typical snowflakes that we think of as snowflakes, like the stars that are in a single plane, columnar and plane crystals, which combine columns and planes. Basically, you had a column start to nucleate and grow here, and then the plane started to form because the temperature and humidity regime changed, which is so cool. Then we have columnar crystals with extended side planes. These images are all from that paper, so again, it's linked down below. And then we've got rimmed crystals, so pretty much any type that are shown, that I just showed, can be rimmed. Basically, here's a needle that has a bunch of little balls on it. I guess that's kind of what I grasped from the rimmed kind of structure. And then you've got a plain star-like snowflake with these little balls on it, and that makes it rimmed. And then we also have irregular, which is what it sounds like. It's just irregularly shaped, not symmetrical, probably formed in variable conditions of temperature and humidity, so it couldn't form just one structure and it came out really irregular. And then a germ of snow crystal is the last category, and that's just a really tiny little hexagon from what I gather from the paper. But anyway, I never expected to have so much to say about just plain old water ice, but apparently it's very cool and very interesting and just surprising how diverse it can be. So anyway, I hope you guys enjoyed that video. I will link my glacial depositional environment videos up here on the screen for you if you want to check those out. And if you want to check out the references I used to make this video, they're linked in my description box below. And with that, guys, thank you so much for watching, and I'll see you in the next video.